Hello, data structures class. This is our video on the binary search tree homework and some tips for implementing it. I'm going to share my screen here and we'll move over to, there we go, our terminal sessions. I'm logged into the Lambda server right now, two separate terminal sessions like normal. Again, when I'm coding, I like to have side-by-side terminal sessions like this. And on the left-hand side, I will open up some Vim windows, and the right-hand side, I'll be running my terminal commands. See, I'm currently in my containers repository, and you can see that I've already merged the assignment with the new BST branch here, so I have access to my files that I'll be needing, this bst.py and this binarytree.py. And then also in the tests folder, there's corresponding files, test cases for both of those files here. We're going to start by I'll open up in Vim my containers slash binarytree.py file. And again, inside of here, there are two classes, the node class and the binary tree class. I liked the font size that I have right now is a nice balance for me between large font that I can easily read and small enough that I can fit lots of things on the screen. So here I can actually fit the entire node class on the screen at once. I used to, way back in the day, use a font size like this, where I could see even more material on the screen. But actually, I have really good eyes, and it's like 1020. But this was too small for me. I was realizing that I was not being as efficient as I could be because I was having to lean into the computer too much to see things. And so I like the larger font size these days, and I use my Vim skills a little bit more effectively to navigate around so that it's not too much of a hassle seeing less things at once. In order to move my cursor efficiently between these classes, again, with the search feature in Vim, you can use any arbitrary regular expression. The up caret matches the beginning of the line, and the word class like this matches my two class definitions, and I can press the in button to move back and forth between those two class definitions really efficiently and easily here. If I wanted to go to the function definitions like this, these methods inside of the classes, my recommended way of doing that, well, there's two ways that you can do that. The first is using slash again to search, so slash and then def to find your function definitions. And now you press in and it'll go through all of the method definitions here, and then shift in, the capital letter N takes you in reverse. Again, the Vim mnemonic, anytime you're moving your cursor, is lowercase things take you forward, either to the right or down, and uppercase things take you backwards to the left and up. So lowercase in short for next, takes you to the next thing that you are searching for, and uppercase N takes you to the previous thing that you are searching for. Another useful navigation tool that I use all the time on these larger Python files is, and I'm going to just type it over here on the right-hand side again, the square brackets. So double square brackets like this takes you to the next top level definition. And it's again, these are sort of like right pointing brackets. The left pointing brackets take you to the previous top level definition. So this is an even faster way to search between your, to select which class you're trying to look at. If you don't want to go to top level definitions, but you want to go to just the next definition period, square bracket in like this will get you going between function definitions as well, even if they're inside of classes. So this is the binary tree class. Again, the binary tree file, two different classes, this node helper class up here and the binary tree class down here. Maybe one last thing I'll remind us about is that in Python, class names use camel case. So binary tree here, camel case, node here, camel case. Everything else in Python, though, uses snake case with underscores because Python is a snake, and functions and methods are the primary things that that you should be thinking about using in Python. These classes, they are important. They're used a lot in Python, but you should also be thinking them of thinking of them as a little bit weird, and that's why they use the camel case instead of snake case. I have my binary tree file open right now. Let's also open up our BST file, :tab E BST. I'm in normal mode here, and so :tab E BST. Whoops, not BST, but containers/BST. And again, notice that I'm using tab completion down here in the bottom left of my Vim window. You can see what I'm typing in, and notice that I'm using tab completion to complete my file names for me, so I don't have to type them out. I don't have to remember exactly how to spell the word containers. So many vowels in there, easy to get confused. And I don't have to make my, I don't know, fingers type too much. They are lazy. They don't want to work. So we'll use tab, make sure we don't get those typos, and we can type faster. And then bst.py like that. I especially use tab whenever I'm getting to the extension part of a file name, like the .py part, because yeah, I don't want to type that in. I hit enter, there we go. Up here at the top now, you can see that I have multiple tabs open, this BST tab and this binary tree tab, and I can press GT to switch back and forth between the two of them. And again, our BST class right here is a subclass of the binary tree class. We also say that BST extends binary tree. So that means as we're working on our assignment, anything that we implement in the binary tree class, we will get inside of the BST class sort of for free automatically. Before I go in and start writing some code here in the binary tree class, I'm going to actually, on the right-hand side, change my branch. I'm going to switch over to the BST solution branch with this git branch. And actually, I think I should probably move this Zoom box down here out of the way. Git, not git branch, git checkout BST_solution. The way I keep all of my projects organized for this class is I have a branch for the assignment that I give to you and a separate branch for the solution. And that lets me keep all of the material in one location. And if I update the assignment, I can easily update the solution using various merge techniques. And yeah, I'm never going to lose the solutions or lose the original problem set this way. And it makes it easy to go back and forth between the two of them. The reason I wanted to check out the solution here was just to give you an illustration of what your final program that you're implementing for this project is going to be capable of doing. And so here I am in my, I've just launched the interactive Python, and let's do an import containers.bst here. With these import commands, it is a little bit weird how Python works. Not intuitive at all. It's one of the things that I dislike about Python. But the first thing over here, the containers part here, this is a folder right here. So on the left-hand side, I'll press Control-Z to temporarily stop Vim. That was Control+Z that I typed. The reason I pressed Control-Z is because if I type FG again, it brings me back to the original files that I had opened here. Let's press Control-Z one more time. And I just want to take us into our containers repository and show that this containers right here matches this containers folder over here. And then if I do ls containers like this, then this BST over here matches this bst.py file. This is how in Python you load other Python files, is through the import command, and then they have this sort of weird convention of everything that's going to be to the left of dots is a folder, and then the very last thing is a Python file with the py, and you never add the .py to the end of the import command over here. I'll go ahead and press enter here, and you'll notice that I don't have access directly to the BST class this way, because I would have to do something like containers.bst.bst to get access to it. And so it's, again, very common to do something like from containers.bst import bst. And now I do have access directly to this BST class. And it's a little bit easier, more convenient to use that way. So this from style import, very common to use on class names. And I don't think there's any official rules about this or official guidance in Python, but it would, at least in my opinion, it'd be considered pretty bad style to use this from syntax on things that are not classes. Like you don't do this for functions typically, but for classes, it's acceptable to do that. So it's again, one of these weird differences between classes and functions in Python. Here, now let's see. And again, these differences are just convention. So like camel case, snake case, just a convention. Whether it's use this kind of import or this kind of import, just a convention. Either way is technically acceptable, but some things are more Pythonic than others. The final BST class, what you're building up to in this assignment, or by the end of this assignment, what you'll have is you'll have a container that is very efficient for certain types of operations. And so if we do something like 1, 2, 3, 4, 5, like this, then we get a, we can see here is our representation, our REPR dunder method representation of the container that was just made. Press the up arrow and then home, taking me back to the beginning of the line, and XS equals that. Let's just store it in this XS variable. And one of the things that we'll be able to do is take the length of this container very efficiently. This length function is actually inside of the binary tree class, not the binary search tree class. But because binary search tree is a subclass, we get access to this length method for free. And this is what we're gonna, by the end of the video, we'll go through and have implemented this particular function here. The main thing, though, that's cool about the binary search tree is that we can do something like if we do 4, or okay, type 3 in XS, like that, we get true. And then, I don't know, let's do 10 in XS, like this, we get false. So the binary search tree gives us a very efficient method for doing this in operation, that with lists, the in operation in takes time O of in general, O of in, or theta in the worst case. And for the BST, binary search tree, and we haven't talked about this fully yet in class, but the runtimes of the binary search tree, what we'll see is that the in is going to take time O of log n. Again, the advantages of the binary search tree, the motivation for it is that it's like binary search. It gives us all the benefits of binary search, but we're never going to have to do that explicit sorting step. And so we'll be able to add and remove elements efficiently and do the lookup operations efficiently. So yeah, the in operation here, this operation that we just did takes logarithmic time instead of linear time, so much, much faster. Okay, that's everything about the what I wanted to show here in the solution. So let's go ahead and run git checkout again, and I will move this maybe in the middle. Hopefully that is not blocking things during the recording. But yes, yeah, we're checking out our BST branch here, back to how we our original problem set up, how your problem will be set up when you start working on the homework. And again, every time I like to, or every time I sort of start a new phase of what I'm working on to help reset my brain, I clear my screen with this reset operation, and just helps me keep myself organized. Back here on the left-hand side, let's type FG again in order to reload these binary tree and BST files. One last thing, actually, with Vim over here, before we get started in earnest, I want to open up my test case files. Anytime when you do colon, oops, yeah, I'm in Vim right now, colon, there we go, colon tab E in Vim, and you open up a new file. So in this case, it's test/test_binary tree that I'm going to open up. The location that Vim puts this file in your tab ordering up here is as the next rightmost file. So my previous tab was in binary tree right here, and it just put it this test over here. Um, Everybody has different preferences for how they like to order their workspaces inside of Vim. Personally, though, what I like is to have my any files that I'm actually working on sort of to the leftmost side, and then test cases things to the rightmost side. I think of the things that I am editing frequently, the more that I'm actually editing a file, I push it more to the left. And the more that I'm just sort of looking at a file or referencing a file, I push it to the right. And for me, that just helps keeps things organized. Whatever works for you, though, you should find just a system and stick with it, and be very consistent. One of the key things about getting proficient with these tools is just developing consistency with the patterns and the techniques that you're using. That way, yeah, consistency is good. So colon-tab E test/test underscore binary tree, and then colon-tab E test underscore BST.ty. And again, GT lets you switch between tabs, cycling to the right, using our mnemonic of capital to the left and up, and lowercase to the right and down. I have G shift T, lowercase g for go, uppercase T for tab, moves me to the left. G lowercase g with a T lowercase moves me to the right. And you don't have to just cycle between tabs. Actually, any of these movement commands, you can press a number before it. And what that means is it'll always go to an absolute position. So if I want to go to the very first tab, I can press 1 GT like this, and it takes me to the absolute position first tab. If I wanted to come down here to, say, line 36, one way I can do that is just typing 36GG, and it takes me to line 36. So anytime you're using any of these movement commands, you can place a number in front of it, and that makes it go to an absolute position instead of the next or previous position. Okay, almost ready now. I want to take a look at this binary tree test case. And again, there's these examples right here, example 0, example 1. And as you're working on any of these programs, any of these test cases, my recommendation is to always start with understanding these examples, understanding some concrete implementation of the data structure before going on to the more general, generic test cases. So in this case, I want to somehow be able to look at these representations in the terminal over here and understand them. In order to do that, I will run Python 3. So Python 3 over here. And then I could do something like import test underscore, and this should be plural, I think, test underscore binary tree like that. And that worked fine. And now I could, if I wanted to access this example 1, I could do test underscore binary tree underscore example 1, something reasonably complicated like that. And it gives me access to this binary tree object right here. This is not a very useful display information right here. And so if I press the up arrow, add some parentheses, press the home key to move to the left curve of the line like that, I can add the string function in front of here to convert it to a string to get a better debugging output, visualization of what this class, what this binary tree here looks like. And again, this string function, what it's doing is I'm going to press 1 GT in my tabs to come over here to the binary tree. I'm going to press slash underscore double underscore str like this so I can zoom into the string functions. Under the binary tree, here's my str function right here. It's kind of inconvenient having that at the very bottom of the window like this. So I'll press ZZ, zeta, to center that on my screen. And we can see that the string function for the binary tree class is just calling the string function on the root. The self, again, means that we're referring to our the instance of this class and not the class object itself. And this particular binary tree only has, or this particular class only has one instance variable created in the constructor right here, this root variable. And this root corresponds to a node class if the tree contains something. And so we just call the string function on that, that root right here. I'll press the in button again to zoom over to the string function, string magic method on the node class right here. Here's the actual implementation of that. It's not, you don't have to try to understand that at all. There's nothing that you have to implement in this node class, but it is important to make sure that you can understand exactly what's going on here in the string representation. We'll do one example of that in this video of how to go from the string representation here to the a useful image diagram of the string, or of the node, of the tree. Each one of these numbers, again, is a node in the tree, and the parentheses here, I selected parentheses because it's kind of like a circle encapsulating that particular number. And if we draw this out, I'll draw it from the top down this time. So we'll start here. This is the very root node of my tree, this one. And I have a window over here that we can do that drawing in. So, and for all of these examples, I would definitely recommend drawing them out something like this so that you can visualize it well. And I put a 6 there. Is the 6? No, it's not a 6, it's a 1. So Control Z, a 1 in that root node right here. And then the after the dash comes the leftmost child, or the left child. There's only 2 children here in this tree. And so this whole thing is the left child. I know that this is the end of the left child because counting my parentheses, we have an opening, close, close, opening, close, close. So this one right here is what matches parentheses. So this is the entire subtree of the left child right here. The root node of that subtree, which is the left child of the 1 over here, is this 2. So I'll draw the 2 as my left child right here. 2. And then the 2 has 2 children. The left child is 4. The right child is 5. 4 and 5, like this. Coming back over here, the very last node here is the 3. And I know this is the right child of the 1 over here because balancing the parentheses, these things over here match. And then this 3 right here is the only thing left for the 1. So back over here, this is what my example 1, I believe this was. Yes, example 1 node, or example 1 tree looks like. Example 1. And I recommend you go through this procedure here so that you have a visual representation of all of the nodes, all of the example nodes here in the binary tree class, so that when you're running your functions, testing them out, making sure they work, you can easily just verify at a glance that it's giving you reasonable or unreasonable results. Looking at how the example 1 here is being created, it's being created manually. There is no function or method being used to create these trees. There is no constructor. There is a constructor, but we're not doing anything fancy in the constructor. We're just individually creating these attributes and then calling the node constructor here to make the node object. So the node constructor is doing something interesting, but the binary tree constructor is not doing something interesting. Okay. So in order to use these examples efficiently, I'm going to want an easy way to be loading them back and forth into my interactive Python. There's a number of ways that we can do that. We've seen one right here where I just run Python 3 by itself and then import the test cases, and then I have access to the .example1 right here. You'll see that in the binary tree file up here, it's actually importing the binary tree and the node classes for us automatically. And so as soon as I import the this right here, as soon as I import that, I'm going to have access to these two classes. I can't just directly type, for example, node, because for the same reasons I can't just directly type underscore example1. I could do something like, whoops, not import, I've already imported test underscore binary tree. Notice that I'm using tab completion here. Tab completion works basically everywhere in the terminal, doing what you would expect it to complete. In this case, the tab completion is aware about what are the attributes of the object to the left, and it completes out of those. So here's the test underscore binary tree dot. I can press tab twice to get a list of all of the things inside of this object over here. And in general, anytime you're doing tab completion, you can always press tab twice to get a list of all the possibilities of things that could complete that tab completion. And here you can see there is in fact a node that I can complete that with. And we can do something like that to create a node 4 object. Let's go ahead and set that equal to node. And then I can do something like node.value here is equal to 4. Node.left is equal to none. Node.right equal to none. This works. This gets you access to the things you need for testing, but it's still a little bit inconvenient because these import commands are kind of a hassle to type in. There's a lot of things going on. Even with tab completion, there's a lot of typing that you have to do. Another alternative is to do some copying and pasting from the left-hand window over here to the right-hand window. Again, when you're copying and pasting from Vim, if you just try to copy and paste directly, you're going to get all these number lines inside of your output over here, which is going to give you weird Python errors like this. So I just copied and pasted, and we get these weird errors. The standard way of doing this is set no number. We'll remove those numbers, and then you can copy and paste without getting those numbers. And in this case, actually, it's still not working though, because the binary tree and the node, they are loaded. We say they're in the local namespace for this particular file, but they're not in the local namespace for the right-hand side over here. So in order to get access to these, I would have to copy, say, this line down here. Now I have the node in the binary tree in the local namespace, and now I can run that and get the underscore example1. Let's make it a string like that. I'm using the home and end keys on my keyboard right now to jump back and forth to the beginning and the end of the line inside of interactive Python. And there we go, we get access to that example1. It's still kind of a pain to copy and paste. There's a little bit less typing maybe going on this way, especially if you get copy and paste this whole thing at once. But we want maximum efficiency in this class, and this is only like mildly, moderately efficient. So in order to find the best possible solution for importing things, I will press Control D. We'll exit out of interactive Python on the right-hand side, and we'll see a better method of importing all of these files. One thing that we can do, so let's say Python 3, let's say I want to open up my 1GT BinaryTree.py file, press GG also just to get to the top of the screen here. You can see that, yeah, let's just directly import this binary tree in interactive Python, Python 3-I, containers/binarytree.py like that, and everything is good. I have direct access to my node object and my binary tree object this way. But what I don't have access to is those examples. So I could start coding and calling my functions easily this way, but I don't have good things to call them on this way. If I try example1, that's not going to work. Press Control D here. The maybe most obvious solution to this, press 3GT and Vim to take me back to binary tree up here. The most obvious solution to this is let's just directly open up the test cases file like this, the binarytree.py test cases, and then we'll have access to everything. I'll press the, well, yeah, I'll just type it out, python3-i tests/test underscore binarytree.py, like that, hit enter, and you see that I'm getting this module not found error. This is happening on line 1. On line 1 up here, let me go ahead and add my line numbers back in, set number. I like line numbers. I like to be able to reference mentally about all these different lines and where they're at. And so here, line 1, we're getting this module not found error containers. One of the reasons why I really dislike how Python handles these imports is because it makes it very non-obvious, like why is it not able to find this module right here? The answer is that, so, and actually, like, so watch here. So this line right here is not able to get us the correct, it's not able to load this. Let's copy and paste that again right here inside of interactive Python. Try that out. You see it's not able to load this. I'll press Control D. Just type in Python 3 without this -i, so Python 3 interactive mode just by itself, copy and paste that same line, and it does work now, and we do get access to those things. And we'll talk about later in the semester exactly why we're not able to get access at this, why we're not able to get access here, but we are able to get access here. We'll talk about that later. Instead, right now, I'll just show a quick shortcut on how you can fix that. So I'll press Control D to get out here, up arrow to get back to this BinaryTree.py file. Press the home button on my keyboard, jump back over here. And I want to, I'll type it out, Python path equals dot space. I'll hit enter and you'll see there's no error message. So this is our new magic incantation for fixing these import errors up here. And give a high-level description of what's going on right now. Basically, so Python 3 here is the program that we are running, and there are two methods of passing in parameters or passing information from the command line to programs. We've talked about these arguments before, these command line parameters that they're called over here, maybe we don't know the details about what's going on, but we've been using them quite a lot in this class so far. This thing on the left, though, is what's called an environment variable. The things to the left of the actual program that you're running are always environment variables. And yeah, we'll talk later on in class about exactly what environment variables are, why you would want to use environment variables versus command line arguments like this. But for now, all you need to know is that this is the magic incantation that will let your, no matter what file you're loading, it will allow this container's import operations to work. One caveat to that, though, and one very common bad practice that I've seen a lot of students doing is that you're running the cd command inside of your repository. Once you get into your repository, you never want to touch that cd command. And I'm going to show you some of the things that go wrong, that happen, that are bad things that result from using that cd command. The first one is that if we cd into the tests library here, and then I try to rerun this command up here, well, I can't just rerun it exactly because you can see that my the file that I'm trying to load right here has the folder tests / in front of it. And so we're currently in the tests folder, so we can't directly run that. So we need to delete that right there. And now we have Python 3-i. I'll go ahead and delete the Python path too, so we can see a little bit better. We have Python 3-i test binary tree like this. And if I hit enter, we see that we're still getting this this module not found error right here. So this is the same thing that we were getting before that we fixed with this this environment variable Python path up here. Control D, up arrow, take me to the home by pressing the home key, Python path equals dot like this. You'll see that that actually doesn't fix the problem now, though. Because I've changed my folder, because I've run the cd command right here, I ran the cd command, changed my working directory to be in the tests path, in the tests folder. Now it's impossible, no matter what I do, for Python to access those containers. And so that's bad. That means testing is much harder now. It's Control D to get out of that, CD dot dot to get back into my home folder here. And we'll do the up arrow until I get back to the good command right here. And now we have access to all of these examples for us, very easy to access. And also things like the binary tree, easy to access. So don't use the CD command after you get into your project. That's lots of, basically all of the tools in the command line like Git and Python, they're all designed so that they're easy to use when you're in the root of your project. But if you're not in the root of your project, then they're not easy to use. So get in the habit of using these relative paths and not just bare file names when you're accessing your files. Okay, I think that's all of the preamble stuff before we actually get into implementing some of the code at last. Over on the left-hand side, 1GT taking me to the binary tree .py file. Do the slash to find, we want to go to the length function. So double underscore len like this and hit enter here. Again, the length magic method, anytime I do the length function like this on a object underscore example 0 like this, the length function here calls the length magic method. In this case, I am getting a type error saying that none type cannot be interpreted as an integer because we're returning none and the length function is required to return an integer. So we're getting this type error right here. I'll fix that really quickly by, so I'm going to use my, to navigate the square bracket m to come down to this length helper function. I'll press ZZ again to center it on my screen. And I want to get my cursor right here so that I can start typing some code for this length helper function. I should mention, why am I in the length helper function? Why am I editing that? Because inside the length function right here, we don't have to edit any code. I've provided a fully working version of this function for you. So we can celebrate that, but it's super trivial because it's just calling this helper function. All it does is call the helper function. And here, the length function is not a static method. This is an ordinary Python method. It takes the instance of the class as the parameter here of self. But really, all of the functions that you're going to be implementing for this assignment, what they really care about is the nodes. They don't necessarily care about the tree, they care about the nodes. And so there's a very common pattern in Python to have a main class that uses a helper class somehow, and the main class just is a very thin wrapper around some static methods that are what the helper class is actually implementing. Okay, so this length function here, it's a static method. We're going to implement this, and we have to implement this because it's being called right here in the length function up here. In order to implement this, I need to get my cursor down here, and so I could type the down arrow like, I don't know, 1,000 times to get there, but that would be a pain in the butt. I could be a little bit more clever and maybe say, oh, this is line 162, so I'll do 162 GG, and that takes me right there. It's still not the ideal thing, though, not my preferred method, but that's definitely a reasonable thing to do. In order to get my cursor back to where it was, I'm going to press the single quotation mark twice. Single quotation mark always takes your cursor back to wherever it was before the previous movement command. So it's like an undo for your cursor movement. Very, very handy. I use that all the time. But the reason I don't like the absolute 162 GG command is because I have to think about like absolute numbers in order to do that. And I have to like move my eye to this line right here and then carefully move it across and see exactly what the number is over here that matches. It takes some time, it takes some thinking, it takes some effort and focus on my part. And I am a puny human. I make mistakes all the time. I don't want to rely on my brain. I want to rely on the computer's brain whenever I possibly can. And so it's much easier for me to think, okay, I just want to move to the end of this function. That means I can go to the beginning of the next function. So square bracket m, and then I can press the Shift O to create a new line, or that in that case wasn't quite in the right spot. Up arrow, Shift O, and there I am. So here, the 4 keystroke command of square bracket m, up arrow, Shift O, and I'm at the right spot to implement. Undo, come back up here. Actually, though, the thing that I probably do, I maybe rely on too much, is I rely on the curly braces to jump down to the next blank line. It says to jump to the next paragraph. Again, the right curly brace, this takes you forward to the next blank line. The left curly brace takes you backward to the previous blank line. So this is a very handy movement tool that I use a lot. And then, yeah, so if we were previously right here, I think we were, so just to Shift curly braces, Shift O, and we're there. It's out of return 1 right here. It's not the correct implementation, but that's okay. We just want to get this type error to go away at first. Here we're getting this warning inside of Vim. Do you really want to write the file? Because we've changed since the last time we've loaded it. I think that's because I was doing the, on the right-hand side over here, checking out the different versions of the files, getting to the solutions and coming back. And so I didn't I didn't close and reopen Vim. I just checked things out. And so it's telling me that the files have changed and just letting me know in case I might not be aware and overwriting those changes. In this case, though, I'm pretty confident that I'm not overwriting anything important, so I'll just press Y to save it. Maybe a last note here that I don't think I mentioned this before. When I was pressing Control Z to pause Vim, you see that it says stopped right here. And if I press FG right now to reopen Vim, you'll notice that I don't have to reopen any of these tabs up here. If I wanted to quit Vim, I can do :Q to quit. This actually quits out of only a single tab. If I want to quit out of all of my tabs, it's :QA, the A standing for all, and it will close all of your tabs. Similarly, you can do WA to write all of your tabs, but I find myself not using that very often because it's much better practice to be saving very, very constantly, and I never have an unsaved tab open. If I quit Vim using the :Q command, I can't do FG to bring it back. I'll have to do Vim containers / BinaryTree.py like this, and I'll only open up the binary tree test for now. Yes. Let's do /dunder length, get me back here, and there we go. There's my return 1 down here. Again, if I try to recall things, rerun things on the right-hand side, we have not reloaded the file, so we're still getting the same error messages that we had before. I'll press Control D to exit out of exit out of Python. Again, that's Control D, Control Delta. And I'll use my up arrows to get back to the previous command, hit enter here, and the up arrows also work fully inside of Python. The Python up arrow environment is totally separate from the terminal up arrow environment. So it keeps your command history separate. Very nice. And now I don't even have to retype anything in Python. I just press the up arrow and I get my command back, and I can test to see if my changes have worked at all. When I'm working on things, especially these large complicated files, I am constantly saving and rerunning things. I probably, when I'm like in a good groove, doing that like 5 to 10 times per minute. If I'm in like my absolute slowest pace, then at most I'm waiting 5 minutes between saving and running things. Probably like once a minute is a typical average. So if you find yourself like typing a lot of code and you haven't saved and ran things, then you are definitely doing something wrong. Okay, so we fixed the little error message here, but it's still obviously not working. This is obviously not what the length is supposed to be doing here. We have some pseudocode here. Our code here is obviously not giving us the right answer right now. I'm going to, let's go GT over here. Let's take a look at our example test cases. And again, we always want to start with our examples, make sure that we have them working for these actual concrete cases before moving on to the other ones. And oh yeah, so the example here is just an empty tree. And so let's just make sure that we're working on the empty tree. That seems like an easy case to work with. And the idea of an empty object is very commonly going to be the base case for our recursive implementations. So always a good idea just to make sure that you can get things working with the empty objects first. Down up here, actually, yeah, so that's what we're testing here, the example 0. And but we're getting the wrong answer right now. That the example 0 has nothing inside of it. There is nothing inside of this. There are no nodes. The root is currently equal to none, and so we should be returning 0. So very easy thing to do. If node is none, return 0 like that. And over here, anytime you're on a line inside of any terminal environment, you can press Control-C to get you a blank line, and now Control-D to get me out of Python, up arrow to rerun interactive Python, up arrow to rerun my test, and we are getting 0 like we expect. So that's good. Press GT coming over here. Let's take a look at example 1 next. And we have this tree that we were previously looking at again right here. We can see that there are 5 nodes in this tree. So we should expect that the length will give us 5. And we will, once I get my implementation working where it's giving us 5, then we can start thinking about actually running the test cases on the proper test cases down below. So taking a look at the pseudo code over here. Well, let's come back over to the image over here that we have of our tree. Anytime that we're implementing any of the functions in this assignment or any functions on a recursive data structure, you should always think about like, so here we're getting we're passing in the root value of our tree. And if somehow our goal is to find the height right now, so find the height. If somehow we knew the height of our left subtree and we knew the height of our right subtree, if we knew these things, then computing the height of the overall tree would be really easy. The overall height is easy. You just take whatever the biggest one of these subtrees is. In this case, it's the one on the left, and you add 1 to it because we're adding 1 new level to our tree. So here, the subtree on the left is 2, and we have 1 up here. So the overall tree would be 3. Height of the tree should be 3. And that's what the pseudocode is telling us to do right here, that we add 1 for our current node, and, oh, whoops. I was talking about the height instead of the length. We're implementing the length right now, not the height. I apologize about that. So back over here, yes, that's what the thing to do for the height, which you'll be implementing on your own. So I guess that's good to think about anyways. I'm going to redraw this. Let's see, 1, 2, 4, 5, 3. 1, 2, 4, 5, 3. The idea for computing the length is similar in that if we knew the length of the left subtree, And we knew the length of the right subtree. And we knew the length of the right subtree. Then computing this length would be easy. So the length of the left subtree, the length equals 3. Here, the length equals 1. And so the overall length is going to be the length of the left side plus the length of the right side plus 1 for this node. So the overall length is just the 1 for the node that you're currently looking at plus the length of left plus the length of the right, like this. And here we go. Let's just implement that. 1 plus the, so here, in order to use this length helper function, that's what I'm going to want to be using. I can't use this length function up here because, well, I'll start by using that length function and we'll see what happens. So let's try just doing the actual length of node.left plus the length of node.right, like this. This is the, like in pseudocode, basically what I want to do. So 1 for the current node. If the left child exists, add the result of length helper on the left child. If the right child exists, add the right of length helper on the right child. So we can we'll break that out so it follows the pseudocode up here a little bit more closely. Result equals 1, and then if node dot left, then result return plus equals length of node dot left. If node dot right, return plus equals length of node dot right, and then return ret. I'll just comment that out. So this is my intuitive high level idea, and then just adding these if statements up here to make it match this pseudocode a little bit more closely. And again, in order to test this, I have to, on the right-hand side, Control D out of that, up arrow, hit enter, and then I can just up arrow again. So we haven't broken the base case. That's good. Up arrow, take that 0, change it to a 1. And we're getting this type error now saying that the object of type node has no length right here. This is happening on line 166. So line 166 right here is where this is happening. And again, anytime you call the length function on something, in this case, we're calling it on node.left. Node.left has type node. I know it has type node because right here, the type error is specifically telling me that the argument to length is node. If I wanted to get more details about that, maybe, I don't know, verify that in a different way, I can add another line up here saying type node at p. Again, I just used my at p macro to add this print statement right here on line 165. And then on the right hand side, Control D, up arrow, run that, up arrow, hit enter. And you can see that right here, it's telling me that the type of node is this containers.binarytree.node class. Again, extremely important as you're working on these large assignments that when you're adding print debug statements that you are telling yourself what you're printing out like this. You can see here that, and I don't know, there's not a lot of output yet, but there's enough output that it's not obvious what's going on, at least to my puny brain. It's not obvious to what's going on here. And so the more you make things obvious to yourself, the more you make it so it's impossible to misunderstand what's going on, the easier your life will be. Yeah, so we're very sure that this is a node that, well, actually, here I'm doing the type of node itself. It's node.left that we're having a problem with. Node.left is being passed inside of here. So let's just add a node.left escape at p here as well. And not node.left, but type of node.left at p, like that. Control D, up arrow, rerun, up arrow, rerun. And now I have, we can verify that both the node and node.left are in fact equal to a node type Very useful to have many things being printed out at various times, and very useful to be telling yourself what those things are that you're printing out. And you don't even have to type more. You actually type less when you do that because it's just at P. Just a little at P makes it no.write type at P. Just at P, two keystrokes is all you have to do to get this excellent debugging information here. When I'm think that I'm done with debugging information, I often like to comment it out just temporarily so that in case I need it in the future, I will be able to come back to it. This also gives me a little bit of a history about what were the things that I was interested in like 30 minutes ago. And sometimes I find that useful. So very rarely do I delete my debugging things entirely. In general, I just comment them out. Okay, so we were saying that the type error here, node has no length. I'm going to do a slash node, come up here to the top, and we can see that it does not, in fact, have the dunder method for len. It only has the init and the str right here. I'm going to use my, let's do it, get back to my length helper here, ZZ, there we go. And where were we? Oh yeah. So the length function right here on node.left is not going to work for our recursive call. We do in fact actually have to call this function itself. The way to do that is, so where's my cursor? There it is. I'll press /len, move my cursor down here. I'll type C, E, C for change, E for the where your current cursor is to the end of the current word. And I will do binary tree dot underscore length helper like so. The reason I did the CE, and I do this very, very often, is because I knew that I was going to have to make this same change in just a couple of seconds, because I'll press undo real quick to get this back. But by doing CE and then typing that all out, all of this change was in just a single command. And so by pressing the dot button, dot reruns whatever your previous command was in Vim, the previous command that made some changes. And so if I press in now for next, that will take me to the next len command down here, the next len word, and I'll press dot, and I don't have to type it out again. Escape : W. Over onto the right-hand side, Control D, up arrow, rerun this, and there we go. Looks like we're getting the right answer, 5. Again, we said that 5 was the right answer for example 1 by looking at our picture, and we evaluated in our head what we thought the right answer should be before actually writing the code so that we would know if we do get the right answer. Let's check the test cases. So over here, and let's see, I see. So I'm gonna do a slash now for my anywhere where we're using the length function or looking for the size. And we can see that these test cases are actually pretty far down here. Last time we or some previous video, I think we saw how to search for your test cases to only run a particular set of test cases. In this case, it's the size test cases right here that we would want to be running. And these are just testing on those particular examples. There's no other like hypothesis test cases here. And I'll just, since I'm already in interactive Python, I can just rerun these real quick and manually verify 1532, 1532, that all those match. In general, for the binary tree, there's no automatic way of inserting things, and so you can't use the hypothesis style property testing. So for all the binary tree test cases, if I type slash and look for hypothesis, you'll see that it's not even found in here at all. Instead, :tab E tests test underscore BST.py, and now here / hypothesis under the binary search tree, there will be an insert function that you'll implement that adds things to the binary search tree. And so here's where the hypothesis test cases will be found. Press GG, come to the top. If you get your things working on all 4 of these test cases, it doesn't guarantee that your binary tree code is correct, but it'll give you pretty high confidence that it's correct. I think unless you're like somehow trying to break it, these are pretty good examples here, and you should have, I don't know, say like 80% confidence that if you're passing these, then the test cases are correct. All of the functions that you're implementing in the binary tree class, again, are going to be also available in the binary search tree class. And so the binary search tree will also use the length function inside of several of its tests here. And you'll have to make sure that or these tests here will also be testing, say, the length implementation in your binary tree using that hypothesis style testing. So at that point, you can be like 100% sure that or maybe not 100%, like 99.9% sure that your functions are implemented fully correctly. So that is the length function. Come down here. The height function is very, very similar, just a slightly different formula that you have to use to implement it. And those are the hard functions, the hardest functions, I guess, of the binary tree class. There's not too many things going on here, but it's not everything that you have to do. There's one last set of functions that you have to implement, and that's this pre-order, in-order, and post-order functions. These are what are called tree traversals, and they're not something that we explicitly talked about in class at all. My expectation is that you will be able to, oops, where did we go? There we go. Come over here to the textbook, and it is section 7.7 that talks about the tree traversals. They're not super hard thing, but I want you to get some practice using your practice reading about data structures without having any sort of explanation about it, because in the future, if you graduate or after this class, when you graduate after this class, you will have to be implementing data structures without having a lecture about them. And so I want you to get practice of being able to just read about the data structure and implement it. So this section's a really good explanation on these tree traversals. It has actual code here that you're welcome to base your solution off of as much as you'd like. Coming back over here, I also have some code that implements these traversals. Here, the pre-order print, in-order print, post-order print functions, these implement those same traversals, and they are correct implementations. And so you can also base your answer off of these implementations here. The only difference between these implementations and the implementations down here, pre-order, in order, and the post order functions methods here, is that these ones will return lists. The ones above just print. In general, a common principle in designing data structures especially, but in programming in general, is that it is much better to return a result than it is to print the result. The reason for that is if you return the result, then you can actually use it and do some processing on it. And one of those processing things that you could do, for example, is print the results. So returning the results is more general, and it's not any harder than just printing it. So always return the results rather than just printing it directly. That's everything for the binary tree. In the, here we go, tab E container / BST.py. In the binary search tree, there's 3 main functions that you will have to be implementing: the find, the insert, and the removal functions. The find, if I search for find down here, There we go. There's find. Find here is implemented, again, following the same pattern of using a static method to help this underscore find function. And the slash underscore underscore, where is it? Insert, not underscore insert, just the regular insert function. There we go. The insert function here is not implemented at all for you, but I would strongly recommend using this same sort of pattern of implementing a static method that's going to help you. That the insert function itself basically does nothing, and the static method does all the real work. There's this insert list function, and in general, the insert list in general, data structures where you can insert one thing will also have a method of inserting many things. And so that's what this insert list does, is that it inserts a large container of things all at once. And there are slightly more efficient ways of doing this, but you don't have to worry about the efficiency. It turns out they actually all have the same asymptotic notation. Efficiency is just constant factor differences. The basic idea of the insert list is that you just a for loop call the insert function over and over and over. The last, let's see, this contains function right here. This is just calling the find function. I should have talked about that a minute ago. This is what actually implements this magic method right here, is what implements the in keyword in Python. So when I was loading up the solution earlier and I did like one in XS, this is the method here that's getting called, and here you can see you don't have to implement it. It's just it'll call your find method automatically. The last major method here is the remove slash. There's the remove function here. And remove is, again, something that I want you to reference in the textbook, how to do it. It's definitely the hardest of all of the functions here. I would not be surprised if the remove function itself took you more time than everything else in the assignment put together. The remove function is in section 7.13 of the textbook. I think they call it delete. Yeah, this self.delete right here is what they are implementing, and I mean the code's not like too bad. You have this code that you can base your solution off of. There's just a couple of different cases that you'll have to handle down here, and but again, I expect you to. I'm happy to answer any questions that you have about it, but I expect you to look at that yourself and try to figure it out yourself. That, I think, covers everything that I wanted that I was hoping, or that I wanted this video to cover for you. I think that'll give you good tools for debugging here and working through your code. Again, on this assignment, don't just focus on trying to complete each of these problems individually. Of course, you'll have to do that, but also focus on making sure that you fully understand how to navigate these files efficiently and figure out what functions affect which other functions, because you will have to do that without collaboration here in just a couple of assignments. But that's it for the video, and good luck on the assignment. Let's take away the screen. Bye-bye. Where are there's